All right. Can you guys hear me and see the screen and everything? Perfect. Okay. Well, thank you guys for having me. Like Dr. Collette said, I'm Spencer Fuston, a PhD student here at the University of Houston, working with Dr. Johnny Wu. I just wanted to start by saying thank you to Dr. Collette and the group as a whole for giving us this opportunity to not only present some of our work, but also arrange some of the previous talks. Very much enjoyed those and have been learning a lot about Canadian tectonics as well as tectonics elsewhere. So what I wanted to talk a little bit about today was some of our work related to structurally unfolding and restoring subducted slabs in the lower mantle below Western North America, with particular implications for the presence of the resurrection plate. But before I get into that, I wanted to start by highlighting the diversity of published plate tectonic scenarios in this part of the world since early Cenozoic time. So the most simple tectonic models of this part of the world involve the subduction of a single mid-ocean ridge residing anywhere from northern Mexico to the Pacific Northwest, all the way over to Western Alaska. And the position of these where this mid-ocean ridge is subducted has primarily been motivated by suites of near trench magmatism present in both Alaska, which motivates the Alaskan scenario, and the Pacific Northwest, which motivates kind of the Pacific Northwest example. However, the challenge that these models have to deal with is that each scenario, whether it's the Alaskan scenario or the Pacific Northwest one, can only account for one of these coeval suites of near trench magmatism at a time. And to try and address some of these difficulties, there's an additional class of plate tectonic model which tries to explain both suites of near trench magmatism at the same time. What we're calling, or what's been called the resurrection plate model, does so by having, instead of a single mid-ocean ridge subducted below Western North America, now there are two mid-ocean ridges, one subducting below Alaska and the other subducting below the Pacific Northwest. And those two mid-ocean ridges bound an additional tectonic plate known as the resurrection plate. An alternate possibility for how to explain these two suites of near trench magmatism, or what we're calling the mobilist model, where there's still a single mid-ocean ridge subducting below somewhere around the Pacific Northwest. But in this scenario, the near trench magmatism in Alaska is explained by translating the Chugach terrain, which is what those intrusions are emplaced into, and moving that down to intercept this mid-ocean ridge. And then as the Chugach terrain migrates to the north over time, the progressive suite of near trench intrusions are emplaced. A very recent suggestion is that during this time period, Western North America was a transform boundary. So really the goal of my talk today is to try and narrow down which of these this wide variety of possibilities are the most consistent with the record of subduction we have from mantle tomography. And the approach that we're going to use to do that is, rather than relying on upper plate geology, we're going to try and reconstruct the subducted lower plate and build a plate tectonic model based on that lower plate reconstruction. So the way that we do that is we use many different mantle tomographies of the upper mantle below Western North America, and we map these slabs, which are still connected to subduction zones below Alaska and the Western US. So we map those slabs in 3 dimensions and then structurally unfold them back up to Earth's surface before inputting those reconstructions into a plate tectonic model. And because our inputs to those plate tectonic models are from mantle tomography, they're actually independent of all of the upper plate surface geology constraints. So as a result of that, we can actually compare and test our tomography-derived plate tectonic models against the upper plate geology and validate them that way. So jumping ahead here, what our results suggest is that a model which includes a resurrection plate is actually the model that's most consistent with the record of subduction that's present in the mantle via imaged via mantle tomography. So I've been talking a lot about near trench magmatism in Western North America. So I thought I should highlight exactly what I'm talking about here. So there are two broad suites of near trench magmatism in the Pacific, or in Western North America. One very famous example in southern Alaska here, where what's called the Sanak-Baranoff suite of near trench intrusives are placed within the Chugach terrain. On the right here, we have distance along the margin plotted against time, where 0 represents a little west of Sanak Island, and 6,000 here is in Southern California here. So what we can see is that this broad group of near trench magmatism is represents that Sanak-Baranoff suite of intrusives. And we can see as they broadly young from west to east and from north to south, and make a very distinctive trend here. And then partially overlapping in the same time period in the Pacific Northwest, there's kind of a comparable suite of near trench magmatism present in Northern Oregon, Washington State, and then in on Vancouver Island, and even more north in British Columbia. So one thing to note is that these two broad suites of near trench magmatism merge somewhere in between 40 to 35 MA, become a single suite of near trench magmatism. So this magmatic record is going to be the main data set that we're going to compare our slab unfolding results against as we go forward. And that's just simply because it seems that near trench magmatism is kind of the most direct record of mid-ocean ridge subduction that we can get at. And the reason for that is that as mid-ocean ridges are subducted, the kind of two opposing plates, as they subduct, tend to diverge within the mantle, opening up what's called a slab window, or essentially just a gap between the two descending slabs. And this allows a stenosphere below the subducting slab to actually upwell through that slab window and mix with the stenosphere above the slab. And this results in significantly elevated heat flows and partial melting in the forearc regions associated with these subduction zones. One really great modern example of a slab window that we can image with mantle tomography is here in southern Chile, where the Nazca and Antarctic plates are subducting below South America. And the ridge between the two is subducting, and we can image this subducted slab and see the slab window between them. So moving back to Western North America, really the slabs that we are most interested in are not the slabs in the lower mantle. Those are interesting as well, but for this talk, we really want to focus in on just the slabs in the upper mantle, which are still attached to subduction zones. These are the ones that we can interpret with the highest degree of confidence, and we can place them into a tectonic model with the highest degree of confidence. So I'm showing here what we're calling the Cascadia slab below the Western US, but also we also looked at we're calling the Alaska slab below Alaska. So if we zoom in on this upper mantle Cascadia slab, we can start to quantify the amount of subducted oceanic lithosphere that's held within the slab anomaly by defining what we're calling the slowest closed contour. And that is the slowest contour which closes around a given slab anomaly. So in this case, it is the 0.1% DVP contour. And the essentially we need to do this to define the edge of these subducted slab anomalies. And once we define that edge, we can really start to quantify the amount of oceanic lithosphere that's held within this anomaly by measuring a cross-sectional area for this given slab and structurally unfolding that and restoring it back to Earth's surface. We restore it back to Earth's surface by assuming an initial thickness of oceanic lithosphere. The thickness we've assumed for this study is 80 kilometers thickness. And so this unfolding process is partially just that balancing of the cross-sectional area versus the length, or the assumed thickness, and getting a length, and partially from a density depth correction that we apply to these cross-sectional area, the cross-sectional area by depth slice. And this is just to account for increased density with the mantle, which are going to compress the slab and make it look smaller than it is. So we put that all together and get a calculated length of oceanic lithosphere that's held within a given anomaly at a given transect. So I'm showing an example of this methodology for one transect, but then we can repeat this process for many transects along strike, up and down the margin. An example of what that would look like is that each of these dark lines here that I'm outlining with the mouse would represent one unfolded slab length from one transect. So, and then we would repeat that for each of these dark lines, and where each of those lines represents one slab unfolding measurement. And then we can take these measurements and input them into a kinematic plate model and develop a tectonic model around them. But I got a little bit ahead of myself. Before we can unfold these slabs, we first have to know where they are and what these slab geometries look like. So to do that, we developed and mapped these slabs in 3 dimensions with what we're calling a mid-slab surface. And that's just the geometry of the exact middle of the slab throughout. So we're just essentially making essentially a structure map of the geometry of the slab. So here below Alaska at shallow depths, around 300 kilometers, you can see that this Alaska slab broadly has kind of a steeply dipping geometry, kind of excluding this area below mainland Alaska, where we have flat slab subduction. And then at deeper depths, around 150 kilometers, the Alaska slab actually appears to shallow out and rest more or less horizontally on the top of the lowermost, or the uppermost lower mantle. Incorporating many of these mantle tomography models together, we come up with a kind of overall mid-slab surface for the Alaska slab that looks like this. So some things to note is that from east to west, the overall aerial extent of the Alaska slab appears to increase. So that is to say that the western part of this slab appears to be more aerially extensive than the eastern part. Another thing to note with the Alaska slab is that, I'll talk about this in more detail in a minute, but we've actually also noted an additional slab, which we're calling the Yukon slab below modern day Yukon, which appears to be disconnected from the Alaska slab and turns out to be a fairly critical part of the interpretation of the tectonics of this part of the world. So I'll show that here in a little bit, but for now we'll move further south to the what we're calling the Cascadia slab and repeat kind of a similar process. So at shallow depths, 300 kilometers depth, we have more or less kind of a normally dipping slab, and then at deeper depths, we have actually kind of a similar story where the Cascadia slab appears to shallow out and rest horizontally on the lower mantle. And then in terms of this overall mid-slab surface map, actually I kind of have a similar trend where the northern part of the Cascadia slab seems to have a much smaller aerial extent than the southern part of the slab. So then, as I mentioned a minute ago, there's really not too much in the way of coherent subducted slabs in the upper mantle below Western Canada. We can see here in a kind of a strike section parallel to the margin, which goes through the Alaska slab here, and then the Cascadia slab here. But you can see both of those slabs you can see fairly well. But then in the intermediate region below Canada, it's much more sparse, and really the only whiff of subducted slab that we get is this Yukon slab here, which is not imaged particularly well in this current tomography, but in a very recent local tomography that I'm showing now, this Yukon slab is much better imaged and appears to be really the only example of subducted slab, which is readily imaged in the upper mantle below Western North America, or Western Canada even more specifically. So one of the main questions we're trying to answer here is, why is there so little slab below Western Canada, and what is the significance of the Yukon slab, right? The only kind of fragment of subducted slab that appears to be there. And we'll try and answer that question as I go. So now we can put all of these mid-surface maps together and actually do the unfolding analysis. So we can see here is that on either of these maps, we have transects 1 through 5, and then 6 through 10 here. And then on the right, we have two plots. Both are the unfolded slab lengths against latitude for the Cascadia slab, or against longitude for the Alaska slab. And within these plots, transects 1 through 5 are notated here, and then 6 through 9, or 6 through 10 are notated here. What we can see is that we've done the analysis with not just one tomography, but as many tomographies as we could get our hands on, which image these slabs well. So each of these data points, or group of data points, represents a different tomography, and we've kind of brought them all together to kind of outline the range of possibilities you get when you unfold these slabs with different tomographies. And what we've done is taken the mean of this range of values for each transect and built that into our reconstruction. So looking at the unfolding results broadly, what we can see is that the westernmost extreme for the Alaska slab and the southernmost extreme for the Cascadia slab are really the two areas where we can unfold the greatest amount of subducted oceanic lithosphere. And then the intermediate regions, as you go inwards towards British Columbia in either slab, show a trend which is a systematic kind of decrease in the amount of subducted slab that you unfold as you move inwards towards British Columbia. So that's the overall trend that you pick up from doing this slab unfolding results. So we're really interested in moving from just the unfolded slab lengths into actually a kinematic model and inputting these restored lengths of oceanic lithosphere into a kinematic model and seeing what that tells us in terms of the tectonics. And that's what we've done here. So on the upper part of the slide here, as I said before, these dark lines, which are plotted next to each other, represent the lengths, the unfolded slab lengths that I just showed you on the previous slide. And we put them all next to each other, and we can draw a polygon around all of these unfolded slab lengths, which essentially represents the total aerial extent of these subducted oceanic plates that we can reconstruct with mantle tomography. So what we can see is that we can start to compare what these reconstructed oceanic plates, how they compare with the upper plate geology in terms of the near trench magmatism. So we can do that by plotting these points of intersection between our reconstructed Kula plate, for example, and North America. So that gives us 1 point here that we can plot. Again, we're just plotting distance along Western North America against time, where 0 is Sanic Island and 6,000 is Southern California. So this first intersection point plots somewhere here for the Kula plate, and then for the Farallon plate, at 60 MA, this intersection point plots somewhere here. So then we can repeat this process for a 50 MA time slice, right? So now these two intersection points of our reconstructed slabs plot here, and repeat that again for 40 MA. Now these two intersection points plot here. So now I'll just finish out plotting all those intersection points, and all those intersection points are actually what bound these colored blue and green areas on the plot down below. And also we've plotted the intersection points of the Yukon slab in purple here. What we can see broadly is that the amount of oceanic lithosphere that we can reconstruct with mantle tomography isn't all-encompassing, right? There are gaps that are left behind after we've reconstructed all of the oceanic lithosphere that we can. And one thing to note is that that unconstrained area that's left over, this white area between our blue, purple, and green areas, actually coincides very nicely with the observed near trench magmatism that is one of these upper plate constraints. So this gives us some indication that perhaps the mechanism that controls the preservation of subducted slabs in the mantle also controls the generation of these near trench intrusions. So this leads us to the interpretation of the gap between our three reconstructed plates representing thermal erosion about two mid-ocean ridges which were subducted below Western North America. And that's what's represented by these black dashed lines here. So we have two reconstruction gaps at 60 to around 50 MA, which then merge going forward in time. So what we've done as a straightforward interpretation of our constraints is we've modeled two mid-ocean ridges within the exact midpoints of these unconstrained areas. These areas that are left unconstrained by after our slab unfolding constraints are taken into consideration. So then we can take these mid-ocean ridge intersection points where essentially at each time along this plot, this black line represents the position along the margin where that given mid-ocean ridge is intersecting the trench. So we can take these ridge trench intersection points and input them into our plate tectonic model, and by doing so, model the positions of these mid-ocean ridges. And that is what's shown, and that's what is controlling where we've drawn these mid-ocean ridges on the maps on the upper part of the slide. So broadly speaking, it seems like a model which involves the selection of two mid-ocean ridges and an additional resurrection plate as a result is the most straightforward way of interpreting our slab unfolding results. And some to make while we're here is that these first modeled ridge positions that I've shown they don't account for any northward terrain translation of the Chugach terrain or any other associated terrains. But one thing to note is that we still achieve a fairly good fit between our kind of modeled ridge trans intersections and the observed positions of the near trench magmatism. So this we're interpreting as kind of a link between the mantle and the upper plate geology. However, we do try and take into consideration how this link would vary if we do assume that the Chugach terrain has been translated to the north through time. And really what we can do to bracket that northward terrain motion is by taking this kind of straightforward interpretation of where the ridge trans intersection was and try and move it to its southernmost well, on the plot here, the lowermost boundary, but on the map, it would be kind of a more eastern position of the ridge, which is shown here. What we can see is that the easternmost position, we can place that ridge before intersecting the Yukon slab, allows for around 1,200 kilometers of northward terrain translation of the Chugach terrain. So even when we consider possible terrain translations, they do still fit within our unfolded slab reconstruction. Another important point that we can make with our slab unfolding results is related to the reconstructed Farallon plate here. And essentially what we can say is actually based on a similar argument to what I just talked about, where the location where we can reconstruct the Farallon plate actually places a southern limit on where we can place this Farallon resurrection mid-ocean ridge. So we can't essentially place this dashed black line further south than our green reconstructed area here, because then that mid-ocean ridge would cross-cut the coherent slab that we were able to restore based on the record of subduction imaged through mantle tomography. So now that we have both our reconstructed slab lengths, and we can model the position of these mid-ocean ridges through time within the areas left unconstrained by our slab unfolding results, we can actually build this into kind of a fully kinematic plate tectonic reconstruction by essentially pinning these ridge trench intersection positions through time, and then assuming geometry for the Kula resurrection Farallon triple junction here. And we just take a very simple configuration, a very simple equal area, equal angle triple junction between them. And then that, in combination with these pinned ridge trench intersection points, actually defines very well the geometry of these two respective mid-ocean ridges. So then the thing to do from there, since we have kind of this fully kinematic plate model now, is to superimpose conjugate seafloor isochrons based on those that are known and observed from the Pacific plate onto our reconstructed Farallon, Kula, and resurrection plates. And this starts to get at the question that I raised earlier when we were looking at the margin parallel cross-section that showed the Yukon slab. And the question was, why is there not more subducted slab below Western Canada, and what is the significance of the Yukon slab specifically? And I think looking at these projected conjugate seafloor isochrons starts to answer that question, because when we look at the position of the Yukon slab, essentially its modern day position projected backward in time, what we can see is that it resides directly below the resurrection plate, but more specifically the western half of the resurrection plate, which happens to be composed of oceanic lithosphere, which is much older than the eastern half of the resurrection plate. So these seafloor isochrons that I've drawn here have their associated ages, which are the ages at 60 MA. So this isochron, for example, was 7 million years old at 60 MA. And then we can see that this other one was 23 MA. So then the eastern half of the resurrection plate is fairly young in terms of the age of the oceanic lithosphere. And then if we compare that to the western half, now we can see that these seafloor isochrons are actually predicted based on the conjugate isochrons to be much older, around 40 MA to 50 MA in age. So this suggests that the western half of our predicted resurrection plate should be much more difficult to thermally erode than the eastern half, which is very young, very hot oceanic lithosphere, which would be very easy to thermally erode. So now we've incorporated all of our slab unfolding results and our model ridge positions into a fully kinematic plate tectonic model. And now I'll just go ahead and show you kind of a video of our fully kinematic plate tectonic reconstruction. So some things to note here. This red polygon represents the present position of the Yukon slab through time. So we just keep that stationary as a reference point. And then this kind of margin parallel white polygon with the red dots inside of it actually represents the Chugach terrain. And the red dots represent near trench magmatism, essentially pinned on the upper plate, and the near trench magmatism will pop in as the video goes, controlled by the age of emplacement of the near trench intrusion. So we'll go ahead and start the video. And what we can see broadly is at the start, the only places of our reconstructed oceanic lithosphere that intersects the margin are the most outward portions around Western Alaska and Southern California. And then as the video went forward, those intersection points migrated inwards towards British Columbia and tracked very well with the near trench magmatism. And now after around 40 to 35 MA, we can actually reconstruct all of the oceanic lithosphere that is predicted from previous plate tectonic models of Western North America. So essentially, the only area that diverges from what we would expect in terms of the oceanic lithosphere that we can unfold is before around 40 to 35 MA. So I'll play that again. Right, so they intersect the most outward portions of the margin, and then both Farallon and Yukon slabs sweep east or inwards towards British Columbia. And then around 40 MA is when our reconstructed resurrection plate is fully subducted, and that's coeval with the time that the Yukon slab is fully subducted. And then again, everything after around 40 to 35 MA is agrees very well with what's predicted by previous plate tectonic reconstructions. So I'll just wait for that to finish here. Cool. So then kind of wrapping everything together here, and going back to that, again, that question about the Yukon slab and its significance with respect to the tectonics of Western North America, our interpretation, which we think is a fairly straightforward interpretation of our slab unfolding results, is that the Yukon slab represents a fragment of the resurrection plate, and more specifically, a fragment of the western half of the resurrection plate, which is predicted to be significantly older than the eastern half of the resurrection plate. And we can kind of summarize that in this kind of synoptic for the slabs being subducted in North America here. So we can see is that we have the Farallon, Resurrection, and Kula plates being subducted with their associated slab anomalies. What you can see is that the western half of the resurrection plate here is around 50 million years old. The eastern half is less than 10 million years old. So as these two mid-ocean ridges are subducted, they both create their attendant slab windows, which bound the resurrection plate in the mantle and actually serve to localize where all three of these subducted slabs are going to be thermally eroded. We can see here is that the Cascadia and Alaska slabs are obviously predicted to undergo thermal erosion, but in comparison to the Yukon slab, which is being thermally eroded from both sides and is composed of very young oceanic lithosphere, we'd actually expect the Yukon slab to be very severely thermally eroded, kind of excluding this older section on the western half of the plate. And this is particularly profound when you consider after 40 MA, after the Queen Charlotte transform has caused slab breakoff and caused the resurrection plate to be disconnected and kind of floating in the mantle, where that thermal erosion can wrap all the way around the slab and really severely thermally erode the Yukon slab. So essentially, we think that the resurrection plate should be expected to leave a very limited record of subducted slab within the lower mantle, just because it's such a young plate that would be so severely thermally eroded. So then in conclusion here, our reconstructed upper mantle slabs support the presence of a resurrection plate starting at around 60 MA and go into 40 MA. We can see here that our reconstructed Kula plate represents around 60 MA of subduction below Alaska, whereas the Farallon plate represents a little bit longer history of subduction, around at least 75 MA of subduction below Southern California. So and then the mid-ocean ridge positions, which are constrained from these unfolded slab results, independently predict the near trench magnetism, which is observed on the upper plate. This leads us to an interpretation of the Yukon slab as a severely thermally eroded remnant of the resurrection plate. And then some kind of additional implications of some of our slab unfolding results is that because of the position of where we can reconstruct the Farallon slab, it actually gives us a southern limit of where we can place this Farallon resurrection ridge, and it actually excludes kind of the famous southern option, the famous Ingebretson paper, at least after 75 MA, which is kind of the greatest amount of time we can reconstruct with our unfolded Farallon slab. So it seems like the Farallon resurrection mid-ocean ridge has to reside in a more northern position since at least 75 MA. And we can bracket possible terrain translations since Paleocene time, which agrees very well with the geologic interpretations of the amount of northward terrain translation that has occurred since that time. And then we wrap all of these constraints into a fully kinematic plate tectonic reconstruction of the resurrection plate. So that's all I have. So thank you guys very much for your attention. I'm looking forward to discussion. Thank you. So then I'll stop sharing my screen.
Thanks very much, Spencer. Okay, I'll stop recording and